Assalamu alaikum. Welcome, dear students, to our fifth part in chapter 17, Newton's laws. By the end of this video, you will be able to define a freely falling body and determine its acceleration. Let's start by having a quick revision for the main objectives of the previous videos. We've studied that inertia is the tendency of an object to resist any change in the state of motion, where the mass is the measure of inertia. Also, Newton's first law stated that an object at rest remains at rest and an object in motion continues in a uniform rectilinear motion unless subjected to unbalanced forces, where the sum of all external forces is equal to zero, and this is equivalent for having a constant velocity. Newton's second law states that the resultant of the external forces acting on an object is equal to the product of the mass of the object by its acceleration vector. The sum of the external forces is equal to ma vector. Let's move on to our new objective. Consider a 1 kilogram hammer and a small light ball as shown in the figure. We will release both objects together from the same position and at the same time. Which one of the two objects do you think will reach the ground first? Do you think that heavier objects fall faster, so that the hammer will hit the ground first? Let's see. Actually, both objects, the hammer and the light ball, falls with the same speed and touch the ground at the same time. But how did that happen and why? Follow with me to answer this question later in the video. Now, what if we take a feather and the same hammer and release them together from the same position at the same time? In this case, which object do you think will reach the ground first? Let's see. We notice that the hammer of a greater mass arrived first, but does this mean that heavier objects are faster? Let's go through with this very simple experiment, and let's do it together. We need to prepare two identical papers, so bring them and follow with me. Are you ready? If not, stop the video and prepare your experimental material. Are you ready now? Let's start. Keep the first paper flat with its regular shape and tear the second paper into two parts. Take only one part and deform it as shown in the video. Then, the deformed part have a smaller mass than the whole flat paper. Now release the two papers from the same height at the same time. Which one will reach the ground first? It is found that the deformed paper, having the smaller mass in this case, reached the ground before. So, in fact, the mass does not affect the motion of a falling body. But how can we interpret this result? Let's see. In fact, what plays an important role in this case is the force of friction or the air resistance. The flat paper has a larger surface area, so it is subjected to a greater air resistance, which slows down its movement. But what if this experiment was performed in vacuum where there is no air resistance effect? Which one do you think will fall faster? Do you think both would fall with the same speed and hit the ground at the same time? To answer all the previous questions, let's observe these two experiments of a feather and a bowling ball in the presence and in the absence of air to better understand the concept of free fall. Then, we will draw out a conclusion concerning the bodies in free fall. This video is taken from the experiment carried out by Brian Cox in the largest vacuum chamber in the world. Let's start with the first experiment where air exists. They took a heavy object like a bowling ball and a very light feather. Both objects will be released from the same position and at the same time to see which one will fall faster. This time the feather fell down to the ground at a slower rate than the bowling ball. But what are the external forces acting on each one of the two objects in this case? Actually, each object is subjected to its weight and to the air resistance. Now the experiment is repeated, but this time the chamber was evacuated from air. So, which object do you think will hit the ground first? Do you think it is the bowling ball? Let's watch again with Brian Cox. The ball and the feather are released from the same position at the same time in the absence of air. 1, 2, 3. Come on, let's see. You can watch their movement filmed in slow motion. Are you expecting for this result? What are the forces acting on each object in this case? There is no air resistance and each object is subjected to its weight only. What can we say about the position and the speed of the two objects at any time? We clearly notice that despite their different masses and shapes, both have the same position and the same speed at any time. We say that the ball and the feather in this case are then in free fall. Then, an object is said to be in free fall if it falls under the action of its weight only. And from the experimental observation, we can conclude that all bodies in free fall falls with the same speed, regardless of their mass, shape, size, or density. Now let's go back to the experiment of the ball and the hammer in the beginning of this video. Even in the presence of air, both fell down with the same speed and land at the same time on the ground. But why? This is because in this case the resistance on the two objects can be neglected compared to their weights. Then the two objects are subjected only to their weight and are considered in a free fall. While in the case of the hammer and the feather, which is so light, the force of friction cannot be neglected for the feather compared to its weight. Then the feather is not considered in a free fall. But do we obtain the same result in theoretical study? Let's start by applying Newton's second law, where the sum of all external forces acting on the object is equal to ma. But a body in free fall is subjected only to its weight. Then W vector is equal to ma vector. But W is equal to mg. Then we can replace it by mg vector, which is equal to ma vector. Now divide the two sides by m, then we will get that the acceleration is equal to g. But the expression obtained here is independent of the mass, which is in agreement with the experimental study. So, all the bodies in free fall falls with the same acceleration, where the motion of these bodies is independent of the mass or any other physical quantity related to shape or size. So all freely falling objects fall with the same acceleration, which is equal to g, under the action of the gravitational force only. For this, g is called the acceleration of gravity or the gravitational acceleration. Now let's check out the unit of g. G is in Newton per kilogram, but N is equivalent to kilogram meter per second square from Newton's second law. Then, if we replace them in the previous unit, which is a Newton per kilogram, we will obtain kilogram meter per second square divided by kilogram. Kilogram eliminated by kilogram gives us meter per second square, which is the unit of acceleration. Then G had the dimension of acceleration. This means that for G equal 9.8 meter per second square, the speed of a freely falling object increases by 9.8 meter per second every 1 second during its fall, and therefore the motion of a freely falling object is a uniformly varied rectilinear motion. It's good to know that a freely falling body does not necessarily mean that the object falls vertically downward. Let's see several examples of freely falling objects. We may have a freely falling objects following an upward vertical motion or a downward vertical motion. Or we may have a freely falling objects following a curvilinear motion. Even the satellite motion is considered as a freely falling object where the forces of friction and all the forces exerted by the sun and the other planet are neglected, and it moves under the action of its weight only. In this year, we are interested only in studying the vertical motion of a freely falling object. Throughout our study in this chapter, frictional forces are neglected unless they are mentioned, and we can distinguish between 3 different cases of vertical motion: the vertical downward motion without initial speed when the object is just released, the vertical downward motion with initial speed, and the upward vertical motion with an initial speed. Note that the acceleration of an object in free fall is independent of the initial speed of the object. Let's practice now by solving the following application. Don't forget to pause the video and try to solve the application by yourself. A boy throws a small ball vertically upward with an initial vertical speed v0 of magnitude v0 equal 4 meter per second at a height of 1 meter from the ground. Neglect air resistance, and it is given that g equal 10 meter per second square. The origin of space is the launching point O. The y-axis is oriented positively upward, and the origin of time is the instant of launching t0 equal to 0. In the first part, you are asked that, or you are told that the ball is in a free fall and you need to justify why. Simply, since in this case, the ball is subjected only to its weight since the air resistance is neglected, then it is falling freely. Now in the second part, you are asked to determine the acceleration of the ball during its movement. Here you need to apply Newton's second law, where the sum of all external forces is equal to ma. The only force is the weight, then mg equal ma. By eliminating m from both sides, we obtain that a equal to g, which is equal to minus 10j. Since the y-axis is oriented positively upward and the g is directed vertically downward, then it is equal to minus 10j, which means that a is equal to minus 10 meter per second square. Now let's move to the third part. Does the acceleration vary if the thrown ball is smaller or heavier? Actually, this information was mentioned a lot in the video. Then the answer is no, it will have the same acceleration since in a free fall the acceleration is independent of the mass of the object. Now we are asked to deduce the nature of motion of the ball during the descending phase and the ascending phase. Actually, in both phases, the trajectory is a straight line and the acceleration is equal to minus 10 meter per second square, which is constant. Then the motion is uniformly varied rectilinear motion. During the ascending phase, while the ball is moving upward, v is positive since it is directed with the positive direction of the y-axis. Then a dot v is negative. Then the motion is uniformly decelerated rectilinear motion. While during the descending phase, v is directed opposite to the chosen positive direction, then v is negative. This implies that a dot v is positive since a is also negative, and the motion is then uniformly accelerated rectilinear motion. Now let's calculate the time taken by the ball to reach the maximum height at s. When the ball reaches the maximum height at s, its speed becomes 0. Then v at s is equal to 0. And since the motion is uniformly varied rectilinear motion, then we can use the time equation Vs is equal to A Ts plus V0, where Vs is equal to 0, A is equal to minus 10 meter per second square, and V0 is given equal to 4 meter per second. Now we replace these values in the equation to obtain 0 equal to minus 10s plus 4, which implies that Ts is equal to 4 divided by 10, which is equal to 0.4 seconds. Then the ball reached the maximum height after 0.4 seconds. Finally, we are asked to deduce, relative to the ground, the maximum height reached by the ball. Also, we need to use the time equation related to the position, where y max, here we are using y since the axis is y-axis, not x-axis, y max is equal to half a ts square, which we have calculated in the previous part, plus v0 ts plus y0. Actually, y0 is equal to 0 since the origin of space is the launching point O at the instant t0 equal to 0. Then we replace the other factors by their values. We obtain half minus 10 multiplied by 0.4 square plus 4 multiplied by 0.4. This indicates that the maximum height from the launching point is 0.8 meter, but we need to deduce the maximum height relative to the ground, so we will add the height of the launching point from the ground, which is 1 meter, and thus we obtain that the maximum height is 1.8 meter. Now let's summarize the ideas of this video. We've studied that an object is said to be in a free fall if it moves under the action of its weight only. During the free fall, the motion does not depend on the mass or the shape of the object. All freely falling bodies falls with the same acceleration, which is equal to the gravitational acceleration g, and their motion is therefore a uniformly varied rectilinear motion. This is the end of part 5. Thanks for your attention.